Swayam Prabha. Digital India. Educated India.
Okay, welcome back, and let's continue the discussion on different reacting system or combustion system. So what we have been talking right now, looking at different kind of combustion system. So broadly they can be categorized in two different category, like internal system and the external combustion system. Most of the practical applications you find in the internal combustion system, and then also the internal combustion system you can also look into different aspect of it, whether it's a steady or unsteady or charge. These are the things that we have already discussed, and then we looked at different kind of combustor like can combustor. These are gas turbine applications, can combustors, can annular combustors. So now we will continue the discussion from there, and then today we will look at the things, other aspect of these things. So just to summarize the whole thing, this is where we yesterday talked about mostly, is that these are all your internal combustion system. So as I said, there are two categories of the combustion system that you can broadly do. One is internal, one is the external, and this is pretty much that internal combustion system that we have talked about. Now the internal system also you can put in two segment. One could be steady flow segment, another could be unsteady flow segment. So this particular table actually summarizes everything for the internal system. So in the steady flow you have gas turbine, you have ramjet, chemical rockets, these are the things. Under gas turbine you could have turbojet. So this is in jet applications, and the work which is produced by the turbine, it is primarily used to drive the compressor. And then you look at the turbofan or turboprop. Turbofan, there is slightly difference from the turbojet. There is a peak fan sitting in front of the engine, which actually sucks the air to the engine. One component goes to core, another component bypassed. So that's why it says partly jet, and the shaft work is drive the fan, and the propeller if it is turboprop. Then you look at the turbo shaft engine, where all the shaft work to drive the propeller, generator or the rotor. Now when you come down to scramjet or ramjet or scramjet, these are mostly for your space applications and all this. There is no compressor or turbine. So that means one of the difference from this gas turbine to ramjet or scramjet, they here no rotating component. So if you are free from compressor or turbine, there is no rotating component, which actually gives you lot of advantage, because these rotating components are always an issue, because then your dynamical system, the behavior of the dynamical system, they create a lot of problem for this kind of GT engines. So here, but the compression is required, so you get the compression done through the ram effect. Now the another category is the chemical rockets, where you could have another two subsection, either solid fuel or liquid fuel. So the solid fuel and oxidant, they are premixed and placed in the chamber, whereas for the liquid fuel you see the fuel and oxidant, they are separated and pumped separately. Now that's all comes under your steady. When you come to the unsteady, you have a premixed charge, non-premixed charge, stratified charge. If it is premixed charge, you have either gasoline engine or gas engine, which is homogeneous charge spark ignition engine. ACCI engine, this is also homogeneous charge compression ignition engine. So, there is a slight difference between these two. One is the spark ignition engine, another is the compression ignition engine. Now, when you have the non-premixed charge, there it is important to note here that air is only compressed, and then this is like your essentially in your diesel engine. What happens? Air is compressed and then you inject the fuel, and then because of this compression ignition, so the ignition takes place. Now, the stratified charge, you have a partially premixed charge, equivalent ratios charge, these are the systems. So, that is pretty much of your internal system. You can classify and look at these things what in practically you see in daily applications. So, now also we talked about some combustors, basically especially which is used in your GT applications, and these combustors are of like one could be can type, one could be annular type, turbo annular type, and this is another schematic of your multiple can. Here you see 1, 2, 3, 4, 5, these are multiple can operation. So, they do take part in the power generation or the thrust generation process. Now, this is another schematic or cut section of the engine with afterburner. So, this is a turbojet engine with afterburner. So, there you see the difference here. You have typically air comes through diffuser, then compressor, then goes through the combustion chamber or the burner, then you pass through the turbine where the expansion takes place, and then after that you have afterburner, which is second level of combustor which is there, where you add more fuel there. So, once you add more fuel there, actually you have an extra burning taking place to generate more power, and then finally you pass through the nozzle, so that this area reduction and all these things produces the high exit velocity. This is quite high, so which is essentially contribute towards the thrust production, towards thrust generation. So, that is how it works. These are the things, some of them already we have discussed, just to show you in a schematically how they look like. Now, once you put down the combustion in gas turbine, you can have other aspect of it, like you have, let us say, spray combustion, because your fuel is liquid. So, this is for liquid fuel, spray combustion. Then you have ignition. So, you can have ignition also, which is another important aspect of it, because without the ignition fuel will not ignite. So, one more important thing is that stability, that is your flame stability. This is quite important when you look at the gas turbine engine, especially in the aircraft application, because flame stability is something which is very, very important. You cannot at given point of time cannot allow to shut off your flame, because then engine will get off and then there would be a huge problem. So, to avoid that issue, in any this aircraft applications, there is a pilot flame sitting there which acts as an igniter. Now this is for combustion noise. Now then you have flame propagation, and obviously there are issues like emission. So pollutant formation, which are CO, UAC, NOx, soot, etc., etc. So these are obvious choice because we have done quite a bit of discussion on this, because you are burning some liquid fuel which is of CX, HY kind of category, hydrocarbon fuel. So once you burn hydrocarbon fuels, the soot, UAC, CO, these are obvious. Then heat transfer is another important aspect of it, because all your combustor valves, they are exposed to high temperature. So there will be huge thermal loading along with the liners. So the heat transfer, and then cooling. So cooling of not only the combustor only, but cooling of the turbine blade also. So this is another aspect. So it is both combustor and turbine. So we need to look at the cooling aspect, because turbine blade cooling is an important area of work which people have been working for few decades, and they come up with a new suggestion or design how one can improve the cooling, and this cooling has a lot of effectiveness in the durability of these blades and all these things. So without cooling, the blades will fail very quickly, which one cannot afford to do that, because the turbine is one of the key component of this whole business, because the turbine generates the power, but this will dictate the design for both upstream and downstream, because turbine will dictate the maximum temperature here, T max. So that will dictate your combustion chamber design. Then combustion chamber, there would be not only pressure, temperature, also delta P across that, which will allow your compressor design, how much delta P I will get across this. So these are, and also the turbine will power the compressor, and if there is a fan sitting there, and then these exhaust things pass through the nozzle and to produce the. So this is in GT application, this is one of the very key component which do take part in the design process actively, because it allows this side of the design, this also dictate the downstream of the design. So there is so this is one has to look at, and that's why now this T max in the turbine, the T max in the turbine is controlled by the blade, the essentially the turbine blade, because this has some material which has a limit for T max, what it can withstand and what it cannot. So this T max will actually control, then this is coming from the material perspective, and that's why one has to cool down that material so that the failure does not occur. So once that is dictated, so you can see that, I mean, in a bigger picture how that dictates the whole business. Now some problems in GT application, So some of them are still an existing problem, some of them are quite a bit of handled. So for example, if you look at NOx control, this is still a problem, one has to actively look at it, and rather the GT industry, they look at it, but obviously NOx is not something which is decoupled from another issue, is the CO or UAC, because the behavior of CO and UAC is slightly different compared to your NOx, and That is why some level of trade off is required, because NOx primarily, if it is not fuel bound, because of the temperature in the post flame region, the thermal NOx formation is quite active, and that is what dominates. But then at the same time, if your temperature is high, CO completely gets oxidized, so that helps. But if you go to low temperature, NOx could be low, but at the same time CO could be quite high. So it's an basically win-win situation where one hand this goes up, this comes down, the other hand it goes down, it goes up. So it's an balancing act between these two. Then your combustion noise, or sometimes people call it hooting. So this is again an instability, but this has been kind of addressed by a lot of GT manufacturer, but still it is not 100% perfect, because some level of noise still comes in. But all said and done, this is something which is actively pursued, and people have come up with some control mechanism so that you can reduce the combustion noise. Then the bigger issue is the soot formation. So this is something one has to work on, because this is a serious problem even today, because any of these gas turbine, when they are flying, if you look at it, or any automobile engines and all this in the back side of it, this is one thing people have to seriously work on this, because the one of the major issue is that these are so small, the soot particles. So capturing soot particles is not that's an easy task. Now through experiments, or rather testing, it is also becoming quite difficult, because the cost involved, manpower involved, fabrications and all these things, and also the equipment which is so sensitive to capture these things. Then the option which is required is the simulations, or high fidelity simulation. But in that case also, so that is the other point, that fidelity of CFD code for combustion. This is another area. So, but even then you have capability, the mechanism or the governing equations and the models which are available even today, they are not that I would say high fidelity model that can capture. So no highly accurate model which can capture. There are models which does predict things correctly, but then when you take it to the real applications, they are so expensive that one cannot afford to do that, and there are simple models, but they are not accurate enough. So it's an again a balancing problem, because some models which can capture it to some extent accurately or reasonable enough accuracy, it can provide you, but problem is that they are highly expensive. So for realistic applications at that level of turbulence or the flow, it is becoming quite difficult. So this is another area where the even CFD is an sort of reached a certain matured state, but for the combustion application still it is requires a lot of essentially the fidelity part, it has to be looked at. Now some development has also, these are some of the problems, few of them are addressed and few of them are still being addressed. Now the developments also there, so we can look at those in gas turbine applications. For example, one try to do that lean premixed combustion. So the lean premixed combustion, which will control obviously NOx, some level of soot, these things would be controlled. But again lean premix means it can goes to some or rather instability. So you can see there, to control these two parameters, you have a solution where you people can go to the lean premixed, but then you come back with this problem. the instability. So, this is an always, as I said, it is a balancing act between one or the other. So, one you can control, the second one will create trouble, or second one you try to control, the other one will be a problem. Then which is another is that you do some sort of an hydrogen doping, which will sort of increase your some sort of an efficiency, control the NOx. So, some advantage it will provide. And the other thing is that higher pressure ratio, and obviously combustor design change. So, you can use some sort of an combined combustor things, whether it is a sort of like annular or cannular tubular, they can be used in that way combiningly, and that can give you better situation. Now, when you go to ramjet kind of situation, it is simple and rather simplest of air breathing system, air breathing engine. Now, only thing it contains some diffuser, that is one thing, CC combustion chamber, and nozzle, exhaust nozzle. So, these are the component it has, but the application is sort of more suitable for high speed, or rather supersonic speed, where Mach number is greater than 1, because the compressibility or compression is done. So, compression is achieved by ram effect only. So, it does not have any rotating component like compressor or turbine or fan or anything such that. On one hand, that is an advantage, because one can avoid these rotating machineries or turbo machineries, because turbo machineries give you a different kind of challenge altogether. So, another obvious is that the fuel injection into compressed flow. So, the flame holders is used to stabilize the flame, and then finally hot product or hot gas expands in nozzle. So, that is how it works. Basically, it gives you an idea about the working principle of this ramjet system, and this is what it is. You can look at this schematic and find out. So, this is the diffusion portion, this protruded portion creates, and because it is an high speed case. So, because of this the diffusion takes place, and then there are flame holders where fuel is injected. This is your combustion chamber. So, it is more like an it is not typically what you see in a gas turbine application. There are can, tube, annular or some kind of a combustor. It is more like an very simple shape, annular kind of shape what the nacelle which has, and there are these are the flame holders. These are flame holders actually. So, one obvious issue which becomes bit critical here is the flame stabilization behind these flame holders, because the airspeed is too high, and due to diffusion it does not come to a level where the flame stabilization becomes. So, that is one of the again challenging area for this kind of application or the ramjet application, because flame stabilization, and then you have also sort of a limitation of the fuel. It's all the fuels, each fuel has its own or different calorific value. So that will tell you what kind of fuel one can use at this speed that the flame stabilization is very effective. So that's an area which requires lot of attention. Then finally it passes through the nozzle to get these things. Now when you come to the rocket application, or rather I would say chemical rockets, what you have two categories of that. One is the liquid fuel rocket. Here we have already told that fuel and oxidizer, they are stored separately and they are stored in a thin wall tanks at low pressure. So your fuel and oxidizer, they are stored in a thin walled low pressure tank. Okay. So they are through the turbines, they are pumped into the turbine, basically the turbine driven pump, they actually pump the thing to the combustion chamber, and there the burning takes place at high pressure. So that is how it works. Then other one is the solid fuel system, where your entire block of the propellant, that is both fuel and oxidizer, so they are stored, entire block of the propellant stored within the combustion chamber. So now combustion actually proceeds from the surface of the propellant. So from the surface of the propellant grain. So one can note that combustion proceeds from the surface of the propellant grain. So that at a given rate depends on pressure and temperature. So and also this combustion rate, so this will have an impact from the pressure, temperature, and also the geometry of the grain. Now this is just to give you an idea what kind of schematic it has, but they are much more complicated than what you see here. These are very simple schematic diagram to just give you an idea how things are. So this is a liquid rocket where there is a pump sitting there, you have oxidizer, you have fuel. So these pumps are actually injecting this into the engine. So this is the engine, and then finally it passes through this nozzle where it generates that huge amount of thrust. And when you look at the solid, this is the propellant block, this is the total propellant block, where fuel plus oxidizer, they are already premixed. Now they are sitting within the combustion chamber and the reaction starts from this surface, and the rate is obviously this reaction rate is depends on pressure and temperature, and specifically the geometry of grain, that is a propellant grain, because the geometry has a huge impact, this grain, the propellant grain, how this combustion will proceed and what will be the rate and But again here the issue is that the solid propellant, the control of these things is not very easy, because they are already within the combustion chamber, and once it ignites, the control of the propellant is not that easy. But whereas when you look at this liquid one, and when the fuel and oxidizer, they are injected separately to the system through the pump, turbine driven pump mechanism, to some extent you can control the flow of these liquids or the fuel or oxidizer, but here there is no such mechanism which exists in the solid case. Once it is ignited, that is a sort of an self driven system or self sustaining system which will keep on burning this propellant. So, the control of these things are not that easy, and then top of that, when that happens, it is quite, lead to instability. So, combustion instability in the solid propellant rocket are quite common, that because the things are not that controlled. So, okay, we will stop here today and continue the discussion in the subsequent lecture.